Hi everyone, this is Aarohi from Pivot Technologies, and in this video I'll explain about what is gradient descent optimizer, when to use gradient descent optimizer, and what is the math behind it. So basically gradient descent optimizer is used to minimize the error by updating a weight of a neural network, right? What we want is we want to minimize the error, right? And how we can minimize the error? By updating a weight, we can minimize the error of any neural network. And if we talk about this gradient descent optimizer update the weight of a neural network through back propagation algorithm. So back propagation algorithm is there, and in back propagation algorithm we have forward pass and a backward pass. In forward pass we give input to our algorithm, and input will pass through several layers, and finally we'll calculate the output. That will be a predicted output of our algorithm, and then we'll check the difference between the actual y value and the predicted y value, and will calculate the loss, right? So after calculating the loss, we go in backward direction, means then we'll use backward pass of back propagation, and during that backward pass we update the weight, and update we will update the weights on the basis of loss function only. So this loss function, error function, act as a guide for optimizer by telling our optimizer whether it is moving in a right direction or not to reach a global minimum. See, what I'm trying to say over here is if loss is increasing, the value of loss is increasing, right? That means we are updating a weight in wrong direction. And if the value of loss is decreasing after we are updating a weight, that means we are updating a weight in a right direction. So that's why I've said like loss function act as a guide for optimizer. So on the basis of loss, we'll see whether we are updating the weights in a right direction or not. So consider this picture over here. So this is a parabola curve, right? So over here, this is the initial weight value. Assume the initial weight value which we are using for our algorithm is this, right? And this is the global minima. Global minima is a point where loss is minimum, means this is the least possible value for error, right? And our target is, our goal is to achieve this loss, right? To achieve at this global minima. But our initial weight value is here, right? And the target is to reach at this point. So over here, the main goal is how would we know whether we have to move in which direction if we want to reach here? Means, consider this picture. Suppose this red point over here, right? Over here. Let's suppose the initial weight value is somewhere over here. So we know that this is the global minima. That means if our initial weight value is somewhere over here, that means we have to move towards left direction. Then only we can achieve this. With then only we'll be reaching this minimal global minima point, right? And let's assume if our initial weight value is somewhere over here, and we know that the global minima is here, that means now over in this particular scenario we have to move towards right, then only we will be reaching at this particular point. So our basically our main intent is to reach at this optimal point, to reach at this global minimum. But how do we know that whether we have to move on left side or right side, means on which particular side we have to move so that we can reach the global minimum, right? So for that I'll be showing you a math proper, I'll show you a proper equation, proper solution. By using that mathematical equation you can easily find in which direction to move if your initial weight is on left side and if your initial weight is on right side. So I'll explain you in some time that, right? So clear till now what we have discussed, that optimizer is used to reduce the error, and how we can reduce the error by updating a weight. And while updating a weight, the main challenge is how do we know like in which particular direction we have to update the weight. And for that I'll show you a mathematical formula. By using that formula we can easily know whether to move in left direction or in a right direction to reach global minimum. All right. So, whenever we use any algorithm, let's talk about back propagation algorithm only. What happen is, first of all, is we have a forward pass. Means we pass input to the algorithm and input travel through network, and then we calculate output, and then we calculate loss. Right? On the basis of loss only we update the weights. So if you're using gradient descent optimizer, so formula for calculating loss is this. Means how we can calculate formula, how we can calculate losses. This summation will run from I is equal to 1 to n. So this n means let's suppose if you have 20,000 data points in your data set, right? Let's suppose in your data set you have 20,000 records. So that means it will run from first record to the 20,000th record. It will run for all the records, right? That simply means in gradient descent optimizer, loss will be calculated on the basis of all data points which are present in your data set. So if let's suppose if 1 million records are there in your data set, so it will calculate the loss on the basis of 1 million records then. And this y is the actual y, and this y hat is a predicted y, and then the whole square. So this is the formula for gradient descent optimizer. So the very important thing to understand over here is that in gradient descent optimizer, we calculate loss on the basis of whole data set. And once we calculate the loss, the next thing is to update the weight. Now, how to update the weight? So this is the weight updation formula for gradient descent optimizer. W new means weight new, means the new weight which we updated weight, right? The new value of weight which we want is, how we can calculate that? Old weight, the initial weight, minus n dl by dw. This dl is derivative of loss, the loss which we have just calculated over here. Dl is a derivative of loss by derivative of weight, and this n is a learning rate, right? Now let me tell you what is learning rate first of all, then I'll explain you the whole formula. So learning rate is simply a learning step to reach your this global minima. Consider this picture. See over here, our initial weight value is here right now, and our target is to reach at this minimal point, global minima, the where the error is minimum. So if you see first few steps, so these steps are larger steps, means we are taking long steps to reach over here. But when we are about to reach this minima, global minima steps, we have decreased the size of steps. So this is called learning rate. Learning rate simply means the steps which you took to reach at this global minima, right? So see over here there are two scenarios. Consider this first picture now. So if you'll see, this is the initial point. Let's suppose our weight value, initial weight value is somewhere over here. So over here, I'm taking long steps, right? Over here, I'm taking long step, means high learning rate. So see, what is happening over here, that from this position, we are directly, now we are not hitting the minimum, we are not able to reach the minimum. Why? Because the steps are very long, and we overshoot this minima, global minima, which is the target where we want to reach. So that means never choose high learning rate, because what will happen is sometime it will not hit the minimal point, sometime it will overshoot this particular point where we want to reach. And what will happen if you choose small learning rate in this case? See, if you choose small learning rate, low learning rate, then training will progress very slowly, because we are taking very tiny updates, we are taking very small steps to reach the global minimum. So it will take very long to complete the training process. So now the question is how to choose a learning rate. So the good way of choosing a learning rate simply is just take the long steps in the starting, but when you are about to reach the global minima, then you can make your steps smaller. So this is what learning rate is, right? So let's come back to this equation only, W old minus N dl by dw. So this is the weight updation formula, means by using this formula we'll get a new weight value. Okay. So the dl by dw in this. in this equation we have this dl by dw hold. What is happening over here? This derivative of loss with respect to derivative of weight. What we are calculating over here? We are calculating derivative of loss with respect to derivative of weight, and this particular thing is called gradient descent technique. So we are studying gradient descent optimizer, right? So what is gradient descent in it? So this, when we are calculating the derivative of loss with respect to a derivative of weight on whole data set, we are calculating this loss on the basis of whole data set. Remember, in just last slide I've told you that gradient descent optimizer calculate this loss function on the basis of whole data set, and we'll be calculating this dl by dw on whole data set, and this particular thing is known as gradient descent in gradient descent optimizer, right? So this is the formula for weight updation. So we have started how to calculate loss in gradient descent optimizer, and then what is the formula for gradient weight updation, and what is learning rate. Till now we have studied this much. Now, see, as I've just told you, we want to update the weight, but how would we know whether to move in left direction, whether to move in right direction to reach a minima point? So, to know the direction, in which direction we want to move, for that only we are calculating this derivative of loss with respect to derivative of weight. So, what I'm trying to say over here is, see, what I'm saying over here, that if we will calculate this derivative of loss with respect to derivative of weight, after calculating this we will get to know, by calculating this we will get to know whether to move in which particular direction, whether to move left or whether to move right if you want to reach the optimal point. So what I'm trying to say over here is, see, we know error is a function of inputs and weights. This error is a function of inputs and weights, means if you will change the input or if you change the weight value, what will happen? Output will change. And if output will change, that means the error will also change, means error is changing, output is changing on the basis of input or weight. So that's why we are saying error is a function of weight, and that's why we are saying over here we are calculating a error with respect to weight, means if will weight change, error will also change, right? So we now I'll show you how to calculate derivative of weight with respect to derivative of derivative of loss with respect to derivative of weight. So see, from last two slides I'm talking about derivative, right? So what derivative is exactly? So derivative simply says what is the change in dependent variable when there is a change in independent variable, right? So see this picture, this is x-axis and this is y-axis. This delta means change, delta x means change in x, delta y means change in y. And I've just told you, like, derivative simply says what is the change in dependent variable when there is a change in independent variable. So that means if there is a change in x, then what would be the change in y? So y is a function of x, because if x change, y will also change. So see, in starting the value of x is this, right? And then we have slightly moved the value of x from here to here. Now this is a delta x, change in x. Earlier delta x value is this, now we have changed the value with a small number, and now the value of x is this. So this is delta x. So when we have changed the value of x, this is the change in y, means on the basis of this is also changing, and we can simply say that the change in y with respect to change in x is approximately equal to derivative of y by derivative of x. Now I'll show you a equation, right? By using this equation we can finally find out whether to move in left direction or to move in right direction whenever we want to update a weight. Please understand this equation very carefully, because this is the main base of optimizer. The main thing is, means people face problem while updating the weight. They are not aware about the concept, like whether to move in left direction or in right direction to update a weight. So this equation will solve all your queries, right? So over here, we have two scenarios. Either we are on the left of the optimal point or we are on the right of the optimal point. So this is the optimal point. Either we are on the left of the optimal point or we are on the right of the optimal point. That simply means the initial value of weight which I choose could be on the left of the optimal point or on the right of the optimal point. And over here we have 4 points A, B, C, D. A, B is on left of the optimal point, C and D is on the right of the optimal point. And these are the coordinates associated with it. A point, this weight. W1 is the weight when at A point, and assume error of W1 is the error at this particular point. In the same way, if I talk about B, what are the coordinates for B? W2 is the weight for B, and error of W2 is the error at this particular position. Same way for C and D. W3 and W4 are the weights, and E of W3 and E of W4 are the respective errors. Now, suppose I'll show you. First of all, I'm explaining you this part, right? So over here, what I'm doing is first possibility is calculating the error with respect to weight at point A. I'm calculating the error with respect to weight at point A. Means I'm considering this point. Okay. So if I calculate, so suppose if I'm calculating over here, if I calculate this error of W2 minus error of W1 by W2 minus W1. So over here, if you'll see error of W2, error of this is W2 and error of W2 is here, and this is W1 and error of W1 is here, right? So we can see here that error of W2 is smaller than error of W1. This is what I've written here. Error of W2 is smaller than error of W1. Error of W2 is smaller than error of W1, and W2 is greater than W1. This is W2, this is W1. So in this direction numbers are increasing. So W1 is smaller than W2. That means W2 is greater than W1. So these are the two scenarios. So that means this is the value which will get over here is approximately it is a approximate value of derivative of error with respect to derivative of w weight, right? If you'll solve this, the value which will get, that value is approximate equal to derivative of error with respect to derivative of w. And in numerator over here we'll get a negative value. Why we'll get a negative value? Because error of w2, the value of error of W2 is smaller than value of W1. So the numerator is negative and the denominator is positive, right? That means dE by dW is less than 0. Why? Because numerator is negative. By this formula, when we solve this formula, numerator is negative and denominator is positive, right? So if we divide this negative by positive, so because numerator is negative and denominator is positive, that's why dE by dW is less than 0. So that simply means if we divide negative value with a positive value, the result would be negative value only. So that means the derivative is a negative value. So over here this derivative is a negative value. So now we know that dE by dW is a negative value. And this is the weight updation formula. The same formula which I've just shown you. WT plus 1 means the updated weight which we want to calculate. And WT means the old weight. Minus N is a learning rate, dE by dW, which we have just calculated over here. Now dE by dW is a negative value, right? Because numerator is negative and denominator is positive. And learning rate is always a positive value. And in formula over here, we have a negative. We have negative over here, and dE by dW is also negative. Two negatives will become a positive. Means when we have two negatives, both negative will give us positive. So that means what I'm trying to say over here is that we positive means we will be going in this direction, we will be going in right direction when initial weight value is a, and if we want to reach at that optimal point o, then we will be adding so value is positive value now, that means we will be going in a positive direction, we will be going in a direction where numbers are increasing, right? That means the value of new weight w t plus 1, this is a new weight, the value of new weight will be a greater value than w of t. And how we know this, that this value will be a greater value? Because by solving this formula, wt minus this formula, de by dw is negative, and we have one negative over here, negative means negative become positive, so that means we are getting a positive value over here. So we can simply say that the previous value will be a smaller than the new value, the updated weight will be a positive weight, a bigger weight value than the previous weight value. I hope this is clear, right? Now let's consider the second scenario over here. So over here what we are saying is, now the second scenario is our initial weight value is right on the optimal point. Now initial value is on the right of the optimal point. Here we are calculating error with respect to weight. We are calculating error with respect to weight, right, at point C. So as we have just calculated over here, same procedure will follow over here, right? So now if we know the difference, if we minus error of W4 minus error of W3 by W4 minus W3, and if you'll see over here, this error of W4, where is W4? Here. Error of W4 minus error of W3. Where is error of W4? Somewhere over here. Error of W4. And error of W3 will be somewhere over here. That means error of W4 is here, error of W4 is here, and error of W3 is somewhere over here. That means error of W3 is smaller than error of W4. This is what I've written over here. Error of W4 is greater than error of W3, which is true, right? Error of W4 is here, somewhere over here, and error of W3 is here. That means error of W4 is greater than error of W3. In the same way, W4 is greater than W3. So W4 is greater than W3 because values are increasing in this direction. So W3 is here. W4 is next to W3. So in this way, that means W4 is greater than W3. So see over here and over here, the scenario over here is EW4 is greater than EW3 and weight 4 is also greater than W3. That means in numerator also will have positive value and in denominator also we have positive value. That means dE by dW is a positive value, means it is greater than 0. In this case, when we are left of the optimal point, dE by dW is a negative value. But when we are on the right of the optimal point, dE by dW is a positive value, is greater than 0. Now let's use the same weight updation formula. Wt plus 1 means the new weight value which we want to calculate. W2 is a old weight minus n dE by dW. And we know that dE by dW is a positive value which we have just calculated over here. And unlearning rate is again always a positive value. Now we have dE by dW is positive and over here we have negative. Positive, negative will become negative. Over here, in this side, dE by dW is a negative value. Negative and negative, when we combine negative and negative, we are getting plus value. But over here, dE by dW is a positive value, and over here we have negative, which will become negative value. So we can say over here, we are getting negative. Over here we are getting positive value, over here we are getting negative value. That means we have to move in the left direction. That simply means new weight value will be a value which would be lesser than the previous weight value. Means let's suppose the previous weight value is 3, then the new weight value will be 2 or 1, but it will be lesser than this. Why this will be lesser than this? Because over here we are getting negative, right? And if we when so simply over here, what I want to say over here is that by using this weight updation formula, the weight updation formula which we are using here and here in both the scenarios, whether we are on the left or the right of the optimal point, this weight updation formula is taking us in the right direction, right? We are always moving towards the optimal point. So this is what gradient descent optimizer is. Thank you.